Welcome to Data Structures and Applications subject. We shall study double-ended queue in this particular session, followed by the maze problem and other very interesting kind of problems. So let me just take you to the PPT now, where we will study about. So we have double-ended queue. We have seen the normal queue where the insertion is done at rear, the deletion is done at front. And we have also seen some other types of queues like circular queue, priority queue, etc. Now, double-ended queue, these are some of the varieties of the queues, of course. And one such variety is called as the double-ended queue, where the insertion and deletion happens on either ends. You can see in this figure that the insertion is happening at front as well as rear. So this is the rear insertion. Similarly, the deletion also happens at front as well as rear. Now, rear insertion is old and front deletion is also old. That happens in normal queue. So we don't need to actually discuss about those two functions, but in order to explain the working of this deletion front and insertion rear, we shall show some of the very important points related to that and how to build the algorithm for the same. Now, in order to understand this insertion and deletion on either end, the queue is considered to be like a circular one here, because so you can see here the dotted lines indicate that it's a folded one, so the thick one is the actual one. So the front pointer and the rear pointer, again we maintain two pointers here, may happen to be such that it may move on either ends. So that's what we are going to study in the subsequent slides. So let's assume that this is the current configuration of the double-ended queue, where we have two pointers, insert and front, and let's assume that there are three elements, 10, 20 and 30. So now, as usual, like normal queue, rear is incremented and elements are added somehow. In this case, probably rear insertion has been done. Well, so now it so happens that assume that I want to insert in the front. So I need to actually move this front pointer to back. Now, supposing if I assume that this is my 0th location, now I would be forced to decrement this front to -1. So which is not acceptable, because array in C or any other language starts from 0 or 1. So let's assume that it starts from 0. So by decrementing front, in order to insert front, it becomes -1. So that is unacceptable. Hence, we have to assume that this actually goes back to the last one. So that means max -1, because the last location is addressed as max -1, or max is the total size of the queue. So that's why this dotted lines indicate that it works on a circular fashion. Now, similarly, the rear, probably if you have some space in the front, it actually comes back or wraps around. So that's exactly what we try to see here. That, for instance, assume that this is the initial configuration of the queue, like 10, 20 and 30. Rear is pointing to this. See, this is the figure which we have shown. Now assume that I want to insert front. So insertion at the front. So front has to be decremented. Now, if, as I said earlier, if it is 0, then decrementing that would cause problems. So instead, we actually need to adjust this pointer or update this pointer front to max -1, which happens to be the last location in the array. OK, so that's what it is shown here. And similarly, element 40 is inserted at rear. See, insertion may happen at rear. There is no problem, because it is working. It's going to work like a normal queue, because insertion at rear is not a big issue. Similarly, deletion front. See, deletion front also there is no problem, assuming that initial configuration front points to 10 and we increment front. So that's not a big issue. But rear deletion will make rear to decrement by 1. So it's not that rear is not going to be affected because of deletion. Now that's gone. So because it's a rear deletion, obviously we are trying to delete 40 and rear has to be decremented. So these are the two operations new, and the old two operations are the rear insertion and front deletion. So the functions corresponding to this is the front insertion, which we need to see. So as usual, the function you can see that exception cases like Q full is again we will maintain a global variable called count in order to maintain that how many elements are currently there in the double-ended queue, and if it is equal to the max, that's the size of the queue, obviously we cannot insert. Otherwise we try to check, because where the front pointer is, and you can see here if it is it's a post increment. So if front is 0, we need to decrement actually, obviously, but if it is 0, we need to make front pointer to go to the last location. That's a wraparound which we have already explained. So you can see that front pointer is set to max minus 1. Supposing if front is not pointing to 0, there is no problem. You can actually decrement. So it's already done, and so pointed by front it is added. You can just make two statements if at all this is getting confused. So here what we are doing is post increment plus checking we are doing together. So that you can actually do it. Supposing if front equal to 0, first check that. Otherwise you decrement front, and then you can make this x to put it in the location pointed by front. So either way it's fine. The idea is if front is 0, we need to make sure that it's pointing to max minus 1. Right. So supposing, of course, because we are adding a new element, so count is incremented. That's the last statement. Similarly, rear deletion is a new function. Now, as usual, it's exactly the same. And when rear is 0, so you have to make it wrap around. Now, otherwise you decrement as usual, and you already saved in the temporary variable pointed by rear, because rear deletion this time, and that you can return. And since you are deleting an element, so count is decremented. So whenever we add, increment count, whenever we delete, decrement count. So that's exactly the new two functions which are to be added into this double-ended queue. Okay. If you follow the slides properly, okay, what is a maze problem? Okay, I'll explain this maybe with another diagram as I've shown just now in the next slide, but in the real world kind of scenario. So first let's understand the problem itself. Right, so what exactly we mean by maze problem? You would have seen, in movies, Hollywood movies, and in other puzzle solving kind of environment where this is something like a puzzle itself, which is called as popularly known as maze problem. Okay, now this is the original diagram which normally people show. That assume that we have a pattern something like this, where we have the thick lines here are called as the walls, and these white ones, the openings are the path which the rat can actually move. Okay, so this is the entry point for the rat, and this is the exit point. Try to understand the problem first. So we are given a board or a scenario or a framework where we have walls and we have openings. So a lot of computer games also you would have seen something like this, but this is a very old popular game. Okay, now maze or the rat enters here, and you should be able to show the path for this maze to come out from this exit point. Like for example, it can enter here, it can go like this, like, okay, I'll just draw this for you. Okay, it could start like this. Supposing it goes like this, I mean, it takes a path like this, and let's say it goes like this, it goes like this, it goes like this, and because these openings, it can actually move. I'm just showing some random path here. Okay, something like this. If it's intelligent, probably it can come out. On the other hand, if it would have taken some other path instead of this, let's take, instead of going like this, if it had come like this, then it would see a dead end. Now, under this scenario, what it should do, it should actually go back. Now, this is where backtracking algorithm, which you will study in next semester, or recursive kind of methodology, which we have, because, for example, it has taken a path something like this instead of going like this. So it has come here and it has seen a dead end. Now it would have to go back to the same point, not to the starting point. It should go back to the most recent one where it has taken a different path. Okay, see, there are two paths available. Instead of going like this, it has taken this blue. So after seeing some dead end, it could happen at any point of time after going through so many, directions. So what happens here? It has to go back to this and then try out some other options if it has. If it doesn't have, then there may not be any path also. But we assume that there is some path available if at all it goes in a proper way. So that's exactly what we are going to solve. So what is the problem now? To summarize, given this board, okay, the walls and the openings, rat entry point is given and exit point is also given. So your job is to inform or find out the path for the rat into this and then come out into the exit point. So this whole thing, the board can be transformed or modeled in terms of a matrix where 0 indicates that any cell with 0 value indicates that it can move. That means it's an opening. Wherever it is 1, it's a wall. You can see it's shaded, gray shaded. So it cannot go into that direction. For instance, assume that it starts something like this location, and it can go like this because 0, 0. It cannot go like this because there is a 1, and it cannot go like this because it is 1. So it has to go like this 0, 0, 0. So instead of going like this, though it's a 0, it's just taking this path. So we have to work out that, or instead of going like this. So there are possibilities that it can go left, it can go up, it can go down, it can go right, it can go diagonally. That's what we're going to show in the next slide, that what are the possible directions a rat can move. So in this case, you can see that 0, 0, 0, it has come out. This assuming that this is my exit point given. So given this, 5 by 5, yeah, 5 rows and 5 columns, and certain cells are 1s and certain cells are 0. 1 indicates that it cannot move. 0 means it can move. So your job is to find out the exact path by which the rat can actually enter and exit. So I hope that the problem is clear. It's not the solution, it's only the problem. Okay, now let's move on to some more basic points. So we are trying to now build the solution process, for which we need to understand certain things. Like as I said, assume that X is the given current position at any point of time for the rat. Okay, so this is my current position. Okay, I'll just erase this. Okay, from this current position, rat can move in the upward direction, which is north, I'll call it, or right, east, west, south, northwest, northeast, southeast, and south. So there are how many? 8 possible directions to which the rat can actually move. 8 directions. These are possibilities. So supposing if there is a 1 here, it cannot move. Supposing if there is a 1 here, it cannot move. If there is a 0, it can move. If it's a 0, it can move. So there are some possibilities. Out of 8 possible directions, it may have 3 zeros and 5 ones. It depends. So the rat can be at any position. If X represents the current position, then it can move all possible 8. So these are represented like this. Now, further, in terms of our array, a 2-dimensional array, we will try to translate these movements instead of these north-south. That's not going to help us in building an algorithm. So what we do is we will translate this in terms of the array indexes. So I indicates the row index, J indicates so this is I, maybe 0, 1, 2 or 1, 2, 3. This is J, right? Okay, so if this is my current position, I, J, right? Rat can move towards right, supposing. So I remain same row, but column is incremented. Now same row, but this way, left side means J is incremented, because if this is 1, 2, 3, this is again 1, 2, 3. Obviously, if this is my current position, left means the column has to be changed, decrement, here increment, J plus 1, because 2 becomes 3, here 2 becomes 1. Similarly, if there is a possibility of movement up, north direction, that means row is decremented. You can see here row value from 2 to 1. That means I is incremented. J becomes same. Column remains same. So similarly, if this way, supposing diagonally, row has to be incremented. Column also has to be incremented. So from 2 it becomes 3. Here again 2 becomes 3. So I plus 1, J plus 1. So that's it. So we can translate the movement of the rat in terms of the array indexes. That's what this figure shows. So let me erase this. So I think that's the explanation given here. So we will call this array as maze 0, 0. That is maze is the complete array. And supposing if it's at this point, it can move this way. If it is 0, it can move this way. If it is 0, it can move this way. If it is 0, not every time, the rat will get all 8 possible directions to move, because if it is on one side like this, end or the corner, then it has only 3 possible movements. You can see here east, south and southeast. So only 3 possible cases. OK, so that also we have to identify. So that we will show in the next slide. So in order to design an algorithm, it is easier to refer to the predefined lookup table, because now we do not know when the maze is here whether we have 3. Every time, instead of calculating it, we can readily get this information from a pre-stored table, which we call it as a lookup table. So how does it look like? It looks like something like this. So supposing if we I have my directions which is specified as 0, 1, 2, 3. So it's indicated here. 0 means north, 2 means it is east, 6 means west, and this is south. You can see south. So north, south, east and west. Diagonal again northeast, all that. So each direction is numbered, because we are going to store this in a structure, and we could actually find out whether the rat can move or not. So based upon these directions, so we will define or declare a structure where we have two members here called vertical and horizontal. So vertical, you can see here -1, -1, and horizontal no movement, that is 0. And supposing if you're talking about 2, direction 2, you can see here horizontal vertical is 0 and horizontal is 1. So we can easily show with 3 values -1, 0, 1. Because that's what the movement actually shows, rat movement. In order to make sure that, for example, you can see here, it's easy to understand here. Third one, that is this one. You can see here both vertical and horizontal should move. That means get incremented. That's why both vertical and horizontal is 1, 1. On the other hand, let's take 0. That is north from this point. North, you can see here vertically it is -1, and horizontally it is 0. So one is not movement, no movement, and another one is a movement. So this I-1 or J+1, J-1, all these things are actually indicated with respect to these structure members, vertical and horizontal. So that's what is called as offsets, and this entire thing is going to be stored in terms of an array of structure where move is the variable. So move of 0 has two members -1 and 0, because remember the movement of the rat is not just one direction, it is two directions which we need to specify. It's a like longitude and latitude, like we normally location in mobile phones, we normally talk about longitude and latitude. So both are important. So similarly here, rat movement is not just one direction, but we need both the direction, vertical and horizontal. So we need that information depending upon the directional value. So where is the direction? Move of 0 will give me the direction 0. Move of 1 will give me the direction 1, and so on. So once we get all this information stored in the form of a lookup table like this, that's nothing but initialized values, because it's not going to change. So depending upon the current position of the rat, given its I, j values in the array, I can easily find out which direction it has possibility to move and how much offset I should provide. So the offset values will be taken from this move array of structures. So if I want to move up, I can easily know that how much to decrease or increase my I and j value. So basically the movement of the rat on the array is actually calculated by using this table. So we'll show further how is it done. OK. So these are the initial values, maximum rows, number of rows, 6 by 6 array. So here I think we have shown 3 by 3. So let's assume that it is a 6 by 6 array. So what is the starting position of the rat row column? Maybe 1, 1. And what is the exit? 6, 6. So I mean, it could change. You can give these values different. You can read it from the keyboard as well. But we are just fixing these values, starting and exit point and the size of the maze board. OK, now we will try to understand how to calculate the next position for the rat to move using the lookup table. So how to calculate the position of the rat from the current position of the rat? So that is, assume that the current location of rat is some row comma, because remember rat keeps moving, so we have to move it. How to move from one position to the other? That's exactly what we are going to calculate here. So let's assume that the current position is some row and some column. For example, I can assume that this is my current one. So 3, 1, 2, 3, 4, 5, 5 by 5 array I've taken just for demonstration purpose. So the current position may be 1, 2, 3, 3, 3. Okay. Now after after getting this value, say current position, now there could be several possibilities, like 8 possibilities or less than that. Now where to move this rat to the next position? So how to calculate this next row and next column? So this one. How to calculate that? So next row can be calculated as current row plus, from the lookup table with respect to the direction and it's vertical because row value has to be obtained. Now column value is the horizontal one, okay, the movement. So from the current column, I can just find out what is my next position in terms of the column value. Okay, let us assume some sample data so that you can easily understand. So let's assume that may 0, represent the top left corner, as I've already mentioned that it's not 1, 2, 3, but let us assume that it starts from 0, 1, 2, 3, 0, 1, 2, 3. So we have current row to 0, 1, 2, 0, 1, 2, right? So instead of 1, 2, 3, I am just assuming that it is from 0. It starts from 0, something like C array again. Right. So 0, 1, 2, 0, 1, 2. So it's 2, 2. You can see current row 2, 2. What is the current direction? It is 0th position. And the next position of the rat using this formula, next row is nothing but what is the current row? 2. Then current direction is 0. And what is the vertical value? If you look see the lookup table for 0. For 0, you have vertical -1 and 0. So you can see here vertical is -1. OK, you can see here it is -1. This is the vertical we are trying to find out. So essentially it becomes 1 and column it is 0. So it becomes 2. So 1, 2. So 1 is row, that is this one. 1, 2, 0, 1, 2. That is this one. So it has to move up. Now we are trying to find out all paths. Remember why this current direction is 0? Because we would always start looking for the possibility of the next position for the rat to move. We start from north. See, like this. So we go like this. You can see numbering is done in the same fashion. So we start looking for this first, next this, next this, next this, and so on until we reach here. That means if we can move here, we will move. If we cannot, try for this direction. If we cannot move again to this, there could be 1, that is a wall. Then you try for the second direction and so on. So that's exactly what we have done here. Now current position is 2, 2 and the next position is 1, 2 because we have started from north, that is 0. So what happens from this? I'm getting 1, 2, that is this is 1 first row and this is the second column 0, 1, 2. So what I'm seeing here is a 1. So this is not possible to move. So I should try for the next one. That is current dot direction is equal to 1 for the same current position. So now the current position of the rat is 1, 2, which indicate that it is moved to north. And if it is legitimate, which means that it should have a 0. OK, if it doesn't, right, if it doesn't, then we have to try for the next direction. OK. Now what we do is, in case if we cannot move, then we will store this return address in the stack, because it doesn't mean that, assume that I try for the next and I get a 0 there, I can move it, but I may go to a dead end and I may have to come back to this position and try for the next direction. That's the idea. So out of all the 8 directions, any directions fail, I need to store that in the stack so that I can try other possibilities after coming back. So it's highly complex recursive mechanism. So the solution process goes like this. If I get a 0, I move to the next position and current position of the rat becomes that. And again, try for the all possibilities. If anything I get 0, again go there, and by luck, if everything is 0, whatever the directions I'm getting, I could possibly reach. So at the in the process, I should check whether I have reached my exit point. So every time you have to check whether that exit point, which we have given as an initialization, see this one, the row column value is equal to the current rat position, so that you can wind up, because exiting from the recursion also is very important. Okay, now what we do is we will not show the algorithm here because that's not part of your this one syllabus. However, I have actually written a program for implementing, based upon this concept. I implemented the maze complete maze problem, the solution for the maze problem, and I will execute that later and show you in a simpler way, like it's not a graphical one, it is just like movement can be shown, the cells with star, a character star. 0 indicates movement, 1 indicates no movement or wall, and star indicate the path. So because we need to find or show the path of the movement for the rat, for example, like this. So how do you show? So instead of the 0, I put a star, all that. So I'll show you that execution later on. But otherwise, the solution process is good enough. We will not go into the detailed, algorithm, etc. But for the benefit of the people who are interested in knowing how is it executed after implementing it in C or C++, I think I should be able to show you in the later class. So let's not deviate from the current topic. That's the idea. So we are just talking about only the concepts here. I hope that the viewers has understood this. Now let's move on to what is known as multiple stacks. Now, in a given array, we have seen how a single stack can be implemented by using just one stack pointer called top. That means push and pop from the same end. See, top is incremented and elements are added, and for deletion, delete pointed by top and then decrement top. So this is very simple and easy to understand. But supposing assume that we are given an array where we should have or accommodate multiple stacks, more than one stack. It could be any number. So how do we do it? Okay, so we need to accommodate many stacks, and since we have multiple stacks, obviously we will have multiple tops. But in this case, one single pointer may not be sufficient, like top or a stack pointer, but we need also the bottom, because remember, don't get confused. It is not that each stack has got a different container or an array. What we are going to do is we are going to implement many stacks in one array. So we need to find out the segmented portion of each stack. Single memory is divided into segments. That means each segment is dedicated for a particular stack, the ith stack, like that. So I think a diagram will help you to understand. So let's assume certain things here. Maximum memory is the total memory size. Supposing if I have 15 locations allocated, 3 stacks, so 5 locations for each stack, something like that. So maximum memory indicates the single array size. Maximum number of stacks, how many stacks you want to implement. It may not be divisible, so whatever is left out will be allocated to the last stack. N is the number of stacks, of course. So maximum stack for each stack. That means maximum memory is divided by n. And top now is not a scalar, now it's a vector, because every stack in this case should have a stack pointer. Every stack should have a stack pointer, so we need an array. Okay. Similarly, as I said earlier, we cannot manage this with single pointer here, but we need one more pointer called B, which is bottom of the stack. Because it's an array, we can store both. We can store the bottom index of each and every stack. So B of 0 indicates the 0th stack bottom value, and top of 0 indicate the 0th stack. What is the value of that particular stack's index? So these two are arrays indicating that for each stack we can store both top pointer and bottom pointer. Again, a figure will help you to understand. Finally, of course, items array, actual items to be stored. Yeah. So now you can easily, and whatever we have said in the previous slide, now it's shown in the form of a diagram. So carefully observe this. We have 1, 2, 3, 4, 5 stacks. Starting from 0, we have 5 stacks. How many locations? That is maximum memory is 0 to 14, that is 15. So 15 divided by 5 is 3. That is the maximum size for each stack. Okay. Right. So each stack should have both top pointer and bottom pointer. Right. So for instance, this stack 0 has the top pointer and bottom, top of 0 and bottom of 0. And similarly, top of 1 and bottom of 1, top of 2 and bottom of 2. And this arrow indicates that the stack grows from lower side to the upper side. For example, top of 0 will be incremented and element will be added. So initially it is pointing to -1. And initially top 1 is pointing to 2. Actually, it's stack 1's area starts from 3 because it's pointing to now 1 less. So that's it. Similar to the first stack, so-called first stack starts from 0. So my top pointer should point to 1 less, which is -1. So I increment first this and then push. So for example, now it's pointing to -1, add 1 to this, which is 0. So now top of 0 will point to 0. Add one more element, then it will be again top of 0 will go here. Bottom will remain as it is here in this position only, because bottom pointer should indicate which is the bottom position, because we need to contain our elements within this boundary of every stack, because same memory is managed for storing multiple stacks. OK, now I'll show you how the figure will look like after filling some elements. OK, so that's whatever is explained is given here. So under overflow, for instance, or empty position, all can easily be shown. When the condition top of 5 plus 1 is bottom, that is -1 plus 1. Sorry, -1 plus 1 is 0. So both top of 0 and bottom of 0 is it has the same value, which means that it is empty. Similarly, this one. So top of 1 plus 1 is 3, so which is the value for bottom of 1. So that's what I said. Initially, the top pointer will be 1 less than the bottom. OK, so you increment top and then start adding. So bottom remains there. So 15 locations divided by 5, you will get 3 for each stack. OK, so how do we initialize? Top of 0 minus 1 is indicated, bottom of 0 is 0, and starting from 1, we can just use the simple formula for all the stacks. So n number of stacks we have starting from 1, both top and bottom can be easily, initialized by using this. For example, maximum is 15 divided by 5, 3 into 1 for the first stack. So it's 1 and 1 less, like that. So top will be 1 less than the bottom. So that's why you get -1 here. Right. So since top of 5 always points to a filled location, the initial value of stack of 0 is -1, 2 that we have already explained. Yeah, so this is the diagram which shows after filling some elements. So how do we show this? As I said earlier, top of 0 was actually pointing to -1. Now after adding 2 elements, let's take that I have added 10 and 11 to first stack, that is stack 0. So top of 0 was -1. Now it becomes 0. Then it becomes 1 because 2 elements are added. Bottom of 0 remains same. So this is the pointers. So top of 0 points to the top of the stack. Bottom of 0 points to the bottom of the stack. So simple. So given the stack number, I can easily extract or pop the element, topmost element from this stack based upon top of 0. OK, next, this stack is filled with some elements, full actually. So top of 2 is pointing to this 5, now becomes 6, 7, 8. Now it's almost full. You can see here. Exception cases can easily be calculated that whether it has come to the full case or not. So pushing and popping can be done in a similar fashion, but given the stack number, stack ID is very important. So the push operation can be designed similar to the one, but we need an extra input called stack ID, obviously, because which stack you want to insert. See, 10 I want to insert in stack 0 and 30 I want to insert in stack 2. So that's the idea. Right. So we have which stack the user wants to push. Secondly, overflow, is not same as the previous one. Obviously, it's not max -1. See, overflow for this stack may be different from the overflow for this stack, right? So unless we come to the, any particular stack, its top pointer, when it reaches to the bottom of this next stack, probably it's very easy. So that's what we are going to show you. OK, assume that we have pushed 2 elements into the stack 0 and 3 elements into the stack 2. All the remaining stacks are still empty. And coming to overflow and underflow. So what is overflow? How do we calculate this? How do we find this after calculation? So supposing let's assume the stack 2 is already overflowing and any new element to be added in stack 2 should result in an overflow. So when top of ith stack, that is second stack, is equal to bottom of I plus 1 minus 1, that's what I said, ith stack, we are talking about second stack. So what is the top pointer of second? Top pointer of second is 8. OK, I will see whether this calculation tallies. And bottom of I plus 1, so that is third one, is actually 3. 3 value is 9, 9 minus 1 is 8, which means that's what I said, that if top of any stack is equal to the bottom pointer of the next stack, which means that we have come to the maximum size for the stack. You can see very easily here, top of this current stack is actually 8 and bottom pointer of the next stack is actually 9. So that means this has grown. This stack 2 has grown and reached to the top. See, this is not yet grown. So top, when it moves here, obviously it's grown full like that. OK, underflow. So if this condition fails, then you can push the element after incrementing the top pointer of the ith stack. Underflow, right. So we have to check what top of I plus 1. That's I think we have already said very easily. Initial, for example, we'll take this. So top of I plus 1, that is 11 plus 1 is 12. So if both are equal, that means it's empty as the bottom pointer. When this is false, there are elements in the stack. Otherwise, it is underflow. That means no elements are there. So we can easily pop the element provided this condition is false. Right. So we have in a similar fashion multiple queues. So same array we have maximum size as 12, in this case 0 to 11, 12, and we shall assume here again 4 queues, Q0, Q1, Q2, Q3, etc. I'll show you. I forgot to mention that you may be wondering the algorithms for this is same, for the multiple stack I'm talking about, but how to actually manage to write all this, you have to modify the existing algorithm of push and pop with stack ID. So I'll show you that again in the form of a program, C program separately. Right, so multiple queues, same array like one full size, that is 12, and you have 4 queues, and we have front pointers and the rear pointers again with an array. So each queue has got both front pointers and rear pointer, and so items, of course, is the actual elements to be stored in this array, and starting from 0 to maximum size or max size minus 1 is to store the data elements of all the queue elements. So it's almost same, except that for front and rear we need arrays because it's not just one queue, we have multiple queues. So this is for 4 queues, it's indicated. And similar to multiple stack, initialization is shown here. For the first one is again front is 0, similar to normal queue 0, and the rear is -1. For the rest of the queues, you can easily do the same fashion like we did earlier, into I and -1. So there in stack, multiple stack, it is top and bottom. Here it is front and rear. Okay, to summarize this part of the stack and queue: normal stack, dynamic, multiple stack. When you talk about queues, different varieties of queues: normal queue, circular queue, priority queue, double-ended queue, and dynamic and multiple queues. So I think in summary, these are the topics which we have discussed. Under this, each topic, the algorithm, etc. Program we will discuss in the next session. Now, thanks for watching, and we will meet again. Thank you. Thank you again.